So last lecture we talked about continuous joint distributions, and we saw how. Let me just show you what I'm talking about here. So last lecture we talked about joint distributions. We went from talking about just discrete to now continuous. And given this example here, we saw how the probabilities now have transformed the geometric significance of a probability of volume underneath a graph, or in this graph representing the joint density function, that represented the probability. So that's like a step up from the single variable or the single distribution function, where the area underneath the curve, the area underneath the PDF was the probability. Now the area underneath the PDF in a three-dimensional space is the volume. So we had to deal with double integrals now. Double integrals now will become a commonplace mathematical technique. And then we also talked about finding the marginal density from the given joint distribution, which is similar to the way we find it with discrete, where if we find the marginal density function for the x random variable, that means that we have to sum up all of the y's and keep x fixed. But in continuous world, in the continuous realm of things, we don't use summation, we use integration. And the same thing goes for marginal density. And then we did more of that calculating probabilities given a joint distribution that we were given. Okay, so we're just going to continue along with that. So the first thing I want to just mention is about independence. So remember, if you recall two events are independent. So two events, A and B, are independent if what is true? Do you guys remember? Remember independence with events? How did we define two independent events? Their intersection equals their multiplication. So exactly what do you mean by their intersection? Just to be a little bit more clearly, it's the probabilities, right? Yeah. The probabilities of the intersection is equal to the probability of one multiplied by the probability of the other. This is what it means to be independent, for two events to be independent. So how do we relate that kind of, what kind of relationship is there now when we speak about independence with two random variables? So two random variables x and y are independent if the probability that x is some kind of a set, like it's part of a set. It could be x equals, and this, again, this kind of notation is a more general notation. So x could be any random variable. As you can tell, I didn't specify whether it's discrete or continuous. As long as x pertains to a set, and this set could be an interval. The set could be specific discrete values. So again, this is just a general way of representing it. So this is X and Y. This is similar to this here, this statement here. This statement here in the world of random variables looks like this. Okay, so then if this is true, and they're independent, then what it will result here is the same thing as saying the probability that X is some part of some set multiplied by probability that Y is in that same set, is in the set B. So it follows, independence of random variables follows from the definition that we spoke of about the independence of two events. Okay. So let me an example of this. So very simply, I'll give you an example. I'm given a joint density function. Joint density function of X and Y. Now, how do I determine whether X and Y are independent? So the question is, are X and Y independent? So then the question becomes, is f of x, y, right? Is this the same as f of x times f of y? This is similar to this here. The joint PDFs have to be able to be, in a sense, multiplied, right? That's what it means to be independent. It means that the probability functions, probability density functions, the cumulative distribution function, if you have a joint distribution, you should be able to have one individually, separately, and if you multiply them, you should get the joint distribution. That's what it means to be independent, mathematically speaking. Now, given our joint distribution function, pardon me, the joint density function, is it possible that this joint density function, is it possible for me to rearrange this in such a way that they have two functions, but one function is purely with x and the other one is purely with y? Do you guys understand what I mean by this? Okay, so let's do this. Let's review marginal density function. What would be? No, I don't want to necessarily solve for any variable. I just want to first find the marginal density function of x. So I just want to find what x would be, right? What the density function for x would be. What would that imply? That would imply that I would do what? I would integrate from negative infinity to infinity of f of x, y, and integrate this with respect to dy, right? With y. and y goes from 0. It says right here, y goes from 0 to infinity. So this is the same thing as saying from 0 to infinity of x times e to the what? To the negative x plus y dy. Do you agree? So we just applied the definition for marginal density function. But then what can we do here? X here, x in this case, and this integral is a constant. You can treat it as a constant. So this becomes x times e to the negative x. Do you guys see what I can do with this here? I can distribute the negative, and then I can separate this. I can use the law of exponents. Same base, right? They have the same base. When you have the same base and you multiply two exponential expressions with the same base, you add the exponents. So look what I could do. I can take this out, x times e to the negative x. This becomes the integral from 0 to infinity of e to the negative y dy. But then what is this? If you integrate this, what does this become? You can actually go and do the integration, right? Which would be what, e to the negative y negative from 0 to infinity. If you approach infinity for this exponentially decaying function, you go to 0. And then if you plug in 0 here, this becomes positive 1. So this equals positive 1. So the density function, the marginal density function of x is simply x times e to the negative x. And then if you do the same exact thing for the other, if you do the marginal density function, oh, and before I go, this here, hopefully you start to now see this kind of integral as more than just an integral. If you study this a bit more, this is the this here is the PDF of an exponential random variable whose lambda or parameter here is 1. Do you guys recall what the PDF is? Is lambda e to the negative lambda x, and this is 0 otherwise, and x is bigger than 0. Remember this? So this is a PDF when lambda here is 1. This is what I get. I get this. But I already know. What do I know? I know that if I integrate from 0 to infinity of lambda e to negative lambda x dx, this has to give me 1 because it's a PDF, and we already showed that. So now you can kind of look at integrals now and see them not necessarily just as merely functions, as exponential functions as they are. You can actually treat this as a probability density function. Do you see how we can go back and forth from probability to the world of integration calculus, vice versa? So now I don't have to touch a thing. I don't actually have to compute this. If I know the PDF, if I can recognize that this is an exponentially distributed PDF where lambda here is 1. And so immediately this will be like summing up all of the PDF, and that should always have to equal 1. Of course, I can do it very easily because it's not a difficult integrand, but there might be some integrands that are much more complicated. But if you're able to recognize it as a PDF, it simplifies, or you can actually avert having to compute anything. Okay, so then now what's the marginal density function of y? Well, same idea, but now I'm integrating from 0 to infinity of f of xy dx. So then this becomes x times e to negative x plus y, right? Dx from 0 to infinity. And I'm going to do the exact same thing. X times e to the negative x times e to the negative y dx. But now the y is what's going to be treated as a constant. And so I can place that y, that expression with the y variable out in front of the integral. And this becomes from 0 to infinity of x times e to the negative x dx. And this is a perfect example as to what I was just saying, referring to you about now recognizing the integrals not in terms of just merely functions, but in terms of PDFs. So if you study this a bit carefully, right, I can actually go and do the integration, which is requiring me, I'm required to apply integration by parts, right? So I would make this U, I would make this dv or v prime, right? And then I would go about doing integration by parts. Or can anybody tell me what this integral here represents in terms of what we've been studying with random variables? No, no one sees it. So whenever you see this e, right? Yeah, lambda is one, but then first of all, what kind of PDF is it? What is this the PDF of? What kind of random variable? Exponential, right? So this is the PDF of an exponential. So it's the same idea, same thing as here, right? E to negative y, e to negative x, right? E to negative x is PDF of an exponential random variable. And it looks like this. F of x is what? E to the negative x, right? When x is bigger than 0 and 0 otherwise, right? Lambda here, in this case, lambda is 1. If you study this, this is the expected value. This is the expected value, but don't we know what the expected value is of an exponentially random variable? Isn't this 1 over lambda? But what was lambda? We know lambda is 1, so isn't the expected value to be 1? So I already know this here will equal 1. Do you guys see that, how I did that? I didn't compute a single thing. I based it off of the knowledge that I had about probability density functions for the given random variable. That's why it's interesting that how now we're able to go from these two different worlds, apparently, right? Integration and calculus, calc 2 with probability. But now look, I don't have to actually compute this because I understand that this is the expected value for an exponentially random variable whose parameter lambda is 1. So immediately, this is the expected value. I already know what it is. It's 1. So I already know that this is going to be e to the negative y. This is the marginal density function of y. Now, I did all of this to show what? I did all of this to show that f of xy is indeed f of x times f of y. It worked out perfectly because the density function of x was x to the e to the negative x. And the marginal density function of y is e to the negative y. If you combine these two things, you get exactly what we started with, e to the negative x plus y. So yes. So the conclusion is yes. The random variables x and y are independent. Do you guys understand the independence? It's just showing that the joint distribution or the joint density function can be written as a product of two functions where one function is purely the x, it has an x variable, and the other one only has a y. So if you can separate the two like this, then they're independent. If you can't separate the functions as a product of two purely uh, different functions like this, x and y, then it isn't. So what's an example of something that's not independent? Um, so if we have a density function that looks like this, which we looked at already, x plus y, and this is 0. This is 0 otherwise. And this is 0 when x is between, x plus y when x is between 0 and 1, and when y is between 0 and 1. So is x and y are, are x and y independent? So is f of x y equal to f of x times f of y? Well, look at the joint density function. It's x plus y. Is there any way at all? There could be, but is there any way that we can create a function that has only x's in it in the expression and only y's in the expression, that when you multiply give you x plus y? Can we separate the variables x and y in a fashion where they're products such as this, that when you put them together gives you x plus y? It looks like it doesn't, right? It looks like it doesn't, but hey, we could be wrong. So what would be the marginal density function for this? And this goes from 0 to 1 of x plus y. And this is dy. This becomes what? This becomes xy plus y squared over 2 from 0 to 1. And what do I get? I get x plus a half, right? We did this one already. And then the marginal density function for the y variable will be the same idea by what? By symmetry. So then I'm asking this question, x plus a half, when you multiply that by y plus a half, does that give me x plus y? And obviously it doesn't. So because the joint distribution, the joint density function of these two continuous random variables is not the result of multiplying the marginal density function of x times the marginal density function of y, then we say that they're not independent. No, x and y are not. So this idea of independence, right, is a mathematical one, and it really just follows from the first definition of independent events that you've encountered in the beginning of the semester. Okay, so now we're just tagging that along to random variables here, the joint distribution. Okay, that's what it means to be independent. Now, based upon that, idea is the next thing here, which is kind of important. It's the sums of independent random variables. Now that we know what independent random variables are, we want to know more about the sums of independent random variables. So for example, let x and y be independent random variables, and then let z be the sum of those independent random variables. And what we want to do is we want to study this a bit more. So we want to uh, let's look at the CDF of Z. So what's the CDF again? The ZDF of Z is equal to the probability that Z is less than some value Z, right? This is just purely the definition. But what is big Z? Big Z is defined as the probability that X plus Y is less than Z. Okay, these are the big ones. These are big. The little z here is small. So this is X plus Y. Okay. And yeah, you can tag along this less than or equal to sign. Now, to compute this, remember, we're dealing with independent random variables. To compute this, however, if we consider them to be continuous, let's talk about continuous. They're continuous. If they're continuous, and the reason why we're going to be dealing with continuous because we're going to be more focused upon continuous random variables instead of just discrete. So when we do this, this is the integral over this region, x plus y is less than or equal to z of the joint distribution, right, of x and y, dx dy. Now, because they're independent, the joint distribution, right, this here can be separated as a product because of independence. So due to independence, we can write this as f of x multiplied by f of y, the joint, the marginal density functions. Okay. Okay. Now, like I said from last time, the difficult part of these kind of double integral problems with probability is understanding the region that you're double integrating over. So this is the region. And remember, this is given by this region here. This tells me the region of my double integration. And to do this, you have to understand the region and know how to form the bounds of x and y. So that's the hardest part. That's the hardest part. So the way I do this is I look at the region, and this region is going to be in the xy plane. Okay. So go to the xy plane. And what would this look like? X plus y. X plus y less than or equal to z. Now, this is the y-axis, this is the x-axis, okay? So normally we would rewrite this as a function of y, right? A function of x. So y is less than or equal to z minus x. Z here can be treated as a particular value, as a fixed value, and then minus x. So then what is this going to look like? This is z, this is z. And then we have a line that goes right through, right? Z is my y-intercept, -1 is the slope. So it's also my x-intercept. And so this is the region. So this is saying y is less than or equal to this. So the region is this here. This is my region. It's all of this. So what are my x values? So then I'm actually not doing this. I'm doing this. I'm cutting it this way. My region, I'm cutting this way. Why am I cutting this way? Because of the order of x and y. So if I interchange the order here, then I can create a different cutting of the region. But if I treat x first and then y, I'm saying where my x values go. My x values go from what? My x values are coming from what? From where? Left to right, correct? But where in the left? The x values are coming from negative infinity. Okay, do you guys see that? Negative infinity, but it goes all the way to what value? What is this here? In terms of y, right? It's z minus y, not z minus x. Remember, we have to write it in terms of y. So this is z minus y. And this is f of x, f of y, dx, dy. And then what are my y values going from? So once this is true, what are my y values going from? All the way from negative infinity to positive infinity. Do you guys see how we did that? Do you guys see? We're taking these strips. This is kind of a strange way of cutting up the region, but what we're doing is we're cutting it horizontally speaking because the x values are ranging, right, from some x value to another x value. So take one of these straight horizontal lines. So this straight horizontal line comes from negative infinity, but then it stops at the value of at a particular y value, right? And so this x value is dependent upon that y value, whatever that is. So it's z minus y. That's going to be that stop of the x value. But then I'm doing this for every y value from negative infinity to positive infinity. That's why these bounds are the way they are. Okay? And because this inside integral is just with respect to x, I can take out the y one. I can take that out. And this becomes f of y times the integral from negative infinity of z minus y f of x dx and then dy. And then this here is the CDF of x. It's the CDF. So this is like the big X. And the input here is z minus y. So another way I can rearrange this is the integral from negative infinity to infinity of f of x, big F, z minus y times f of little f of y dy. So a lot of this is just in generality, okay? So what we just discovered was the cumulative distribution function of x plus y. And this here is known as the convolution. The convolution of the distributions f of x and f of y. And the reason why we write it this way is because once we have the cumulative distribution function, we can find the PDF, the joint distribution function, by taking the derivative. So if I want to find f of x plus y of z, I take the derivative of the cumulative distribution function, and I write it, and I find the derivative in terms of z. So this is really taking the derivative with respect to z of the integral from negative infinity to infinity of f of x z minus y f of y dy. But we can take, this isn't, we're taking the derivative of this integral, but this integral is with respect to y, and I'm differentiating this with respect to z. If I have, yeah, with respect to z. So then I can rearrange the integral sign with the derivative. And when I differentiate, um, the cumulative distribution function of x with respect to z, I get the PDF instead. Which is, yes. So then that's the reason why we wrote the cumulative distribution function like such, as such, because then I can find the PDF. And again, that's just really embedded from the CDF. So this is a little weird at first. Eventually, what we're going to be talking about are going to be called independent nodes. The sums of independent, so it's going to be the independent and identically distributed random variables. IID are commonplace when dealing with joint distributions of random variables. Okay, so I'll give you an example of this. So let x and y be independent random variables, both uniformly distributed on 0 to 1. Calculate the probability density of x plus y. So I want to find what is the probability density, which is really f of x plus y. Right? I would use just a f of x plus y a. So again, this sum, I can treat this as a, so let's use z for now. I can treat this as a variable in itself, a random variable in itself. It's a sum of two random variables, but now I can treat that as a single one. Okay. And then what do we know about the x and y? They're all independent, right? And they're uniformly distributed. So the PDF of x, and we're using z as an input, so let's use z. So the PDF of z is what? It's 1 when z is between 1 and 0, right? This is the uniform, and 0 otherwise. That's what it means to be uniform. And then same thing goes for y. Y of z, the specific value z, is 1 when z is between 0 and 1, and it's 0 otherwise. Okay, so then what is the sum of z according to our formula here? Well, this is the integral from negative infinity to infinity of what? Of f of x z minus y times the probability of f of y dx. In this case, dy, right? Okay. Now, what is f of y? And again, this is just for the y's, right? The y goes from 0 to 1. Y is between 0 and 1. So this integral here is from 0 to 1 of f of x z minus y times f of y dy. So let's see if yeah. So f of y is exactly what? Hmm. Hold on 1 second, guys. Let me um yeah, so y plus a half. So the thing is that these are uniformly distributed random variables, right? So anything you plug into Z or to the input of your um, PDFs, right? As long as it's between 0 and 1, your output will always be 1. So these are essentially just 1. This is equal to 1, right? That's when Z is between 0 and 1. So essentially, you're saying this. You're saying 1 times 1 dy. So it's really just this dy. Um, but the problem or the difference is that um, your z value can be something between 0 and 1. So this gets a little strange to say, but this upper integral becomes z. And so when you take the antiderivative of a single one here, this becomes y from 0 to z, and this just gives me z. And I think there's something up with this. Yeah, this can be a little, so the PDF is z. Um, the PDF is of x plus y at z is z when z is between 0 and 1. Now, the reason why we're specifying this is because in reality, what we're saying, we're really talking about x plus y, okay? And the reason why I use z is because we said that z, big Z, is equal to x plus y. So this is really about big Z, the sum of x plus y. So what if x, whatever x is and whatever y is, when you add them up, give you something smaller than 1? That's what we're saying. And then, so think about if x can be anything between, remember, x and y are uniformly distributed. If x could be anything between 0 and 1, and y could be between anything between 0 and 1, what's the maximum that x and y can be when you add them up? When you add them up. So z can be as big as 2 and as small as 0. So that's now that's the difference, you see? So then what happens when z is a bit more than 1, but less than 2? So that's the problem here. So according to our formula here, we have the integral of, it's the same thing, right? F of x z minus y times f of y dy, and dy goes from, so the upper bound here is 2, and then the lower bound here is in terms of y is z minus 1. And this is 1. and this is 1. So we're really integrating from this, z minus 1 to 2 of dy. So y goes from z minus 1 to 2. I get 2 minus z minus 1. Wait, pardon me. This should be 1. It's 1 because y ranges from 0 to 1. Z ranges from 1 to 2, but y ranges from 0 to 1. And then, yeah, so that makes a bit more sense. So this is 1. This is 1. This becomes 2 minus z. So this occurs when z is between 2 and 1. And so what we just found was that f of x plus y equals z depends upon what z is. So when z is between 0 and 1, then f of x plus y was what? Was simply z. But then when z goes from 1 to 2, you get 2 minus z. And then it would be 0 otherwise. And when you graph this, if you graph this here, this here becomes a straight line here, just going through, right? But then after, okay, this is like the z axis here. This is like the z. And then after that, after 1, it becomes 2 minus z. So it's supposed to be a straight line from 1 to 2. This should be 2, not z. And this should be the PDF. This is the PDF. And you can study this and see that the area underneath this is indeed 1, right? Base, this is a triangle base 2, height 1. So the area underneath is going to be 1. So this is the convolution. This is the convolution of 2 uniform random variables on 0 to 1. Does this make sense? Or does this need a bit more like massaging? It's hard to comprehend, huh? Yeah. Yeah, we need a bit more examples. So we only have a few 15 minutes left. So I will definitely come back to this idea of the sums of independent random variables. But before we expound upon that a bit more, I just want to talk about conditional. So remember I told you that all of this stuff is going to pop out again, the things that we learned before. So conditional probability is pretty much the same thing that you've already talked about. So recall what is conditional probability. When you say A given B, you guys remember this? This equals what? the probability that A intersect B divided by the probability of B, right? That was conditional probability. It's the same idea. It's the same exact idea for random variables that are jointly distributed. So I'll give you the discrete version and also the general version, the continuous version. So the discrete version we usually use P, right, for discrete. So if we have, for example, we're going to be writing this. If X is given Y, then we're going to have this little notation here. It's a lot of dashes like this. X given Y, X given Y. This is the same thing as saying the probability of X is equal to X, comma, Y is equal to Y, divided by the probability that Y is equals Y. It follows exactly from here. It follows. Same exact thing. And then for, yeah, so a lot of this is just notation here. So this is P of X, Y. This on top here is the same thing as this. And on the bottom here, we normally specify that we're dealing with the random variable being Y. So we specify this being Y. And then the continuous version is very similar, except that we use, instead of P for PDF, right? This is a PDF. This is a PDF. We use little f. And it's the same idea. We're going to use f of x, y, the joint PDF, divided by the marginal PDF of y. Same idea. The difference is that with continuous, it's kind of sometimes awkward just to deal with the PDF alone. So we talk about the CDF. But regardless, this should be it. So then if I have it the other way around, y given x, this would be y given x. Still, the top will still be f of x, y, the joint distribution. And I'm going to divide that by the marginal distribution, okay? So this is joint. These both here are joint. The joint PDF. And this underneath here is the marginal PDF of y, and this is the marginal PDF of x. Same thing goes for up here. This is the marginal PDF of y, and up here is the joint PDF of x and y. So I'll give you an example of each. So if I have an example, example of the discrete. So I'm going to actually define for you. This should be called a PMF, pardon me. PMF is only for discrete. PDF is for continuous. So let x and y be discrete random variables with a joint with a joint probability mass function given by, so I got P of 0, 0. This is 0 0.4. P of 0, 1. 0 0.2. P of 1 comma 0 is 0 0.1. And P of 1 comma 1 is 0 0.3. Okay, so this is an actual PMF. If you were to add all of these probabilities up, you would get 1, which is exactly what's expected from a PMF, right? So this is the PMF. It's explicitly defined of X and Y. Now, what I want to do is I want to find, compute the conditional probability mass function of X given that Y equals 1. So what I'm really finding is this, the probability that X given Y. I'm finding this. That's what I want to find. So what is the formula for this? It's the probability that X equals little x given that Y equals 1 over the probability that Y equals 1 of your random variable being Y. So again, this is the marginal, right? This is the marginal PMF. How do you get the probability that Y equals 1? Mir? Do you have a hand raised? Sorry, I can't hear you. What did you say anything or no? No? Okay. So what is P of Y? How do you find the PMF? Or you can type it in the chat. So do you guys remember how to find the marginal PMF with discrete? Add up all the columns for Y equals 1. That's right. So this is like saying the probability of 0, 1 plus the probability of 1, 1. As long as you have Y equal to 1, just add up all the X's. Well, in this case would be what? 0 0.2 plus 0 0.3, which is 0 0.5. Shouldn't it be P at Y given 1 given X? I think Mir, you're thinking of Bayes formula. Bayes formula does that little switch in the numerator. This is simply conditional probability. Oh, yeah. So if that's the case, so this is a little the mistake. It should be just a comma. It shouldn't be a slash like that. So that was my mistake regardless. Yeah. So this is just a definition, right? So first we're finding this here on the bottom because that's an easy one. That's saying what's the probability of just getting Y equals 1? Well, you just add up the ones that have Y equals 1 to, and then everything else. We're just accumulating those. And that should be 0 0.5. Now, what's the probability that x equals x, y equals 1? Well, x can change, right? X has two values, either 0 or 1. So to find this specific PMF, I want to find the probability that x given y is 0 given 1. And I want to find x given y, 1 given 1. That's what I'm going to do, which is the same thing as saying the probability that x is 0, y is 1, divided by that y is 1. And this is the same thing as saying the probability that x equals 1, y equals 1, given that y over the probability that y equals 1. But what is 0, 1? I have that. It's 0.2 over 0.5, which is what? 2/5. And then 1 given 1 is what? 0.3 over 0.5, which is 3/5. So I found it. This is my PMF. So the PMF of the conditional probability of x given y equals 1 is given by this. X given y, 0, 0 given 1, that's 2/5. And x given y, 1 given 1, 3/5. And then you can do the same thing for x given 0. Do you guys see how we're doing this? We're creating a PMF based upon the joint PMF. And do you see here, this PMF is indeed also another PMF because when you add these up, you get 1. So in this world, it's in itself is a PMF. Are we good with this? Okay, and so for the last example, I want to look at the continuous case. So this is discrete. How about the continuous case? So let the joint density of x and y be given by this joint density function okay, and I want to find compute the conditional density function of x given y equals a particular y value. So find a conditional probability of this. What I'm finding is f of x given y, x given y. But this formula is found if you find the joint PDF of x and y, and you divide it by the marginal of y. Do you see how this is like reminiscent of the PMF version? It's identical. It's just that one of it, the one case that we had before was discrete. So we're dealing with summations. In this case, we're not going to be dealing with summations. We're going to be dealing with integrals. So how do you find f of y? Again, this is the marginal. This is the marginal density of y. So how do we find the marginal density of y? If we have a joint density function. So you find it by taking the integral from negative infinity to infinity of the joint. And you're doing this all through the x's. So you're integrating through all the x's. And the joint here is 12, 5, x, 2 minus x minus y, dx. And dx goes from 0 to 1. So integrate. This becomes what? 24 fifths x minus 12 fifths x squared minus 12 fifths xy dx from 0 to 1. So this becomes what? 12 fifths x squared minus 12x cubed divided by this becomes 4 fifths minus 12x squared. This becomes 6 fifths squared y from 0 to 1. You plug in wherever you see the x, you plug in 1, and if you plug in 0, they all go away. So I get 12 fifths minus 4 fifths minus 6 fifths y. Subtract this and you get what? You get 8 fifths minus 6 fifths y. Right? This is the marginal. And then what was the top numerator? So f of x given y, x given y is equal to the joint. The joint is 12 fifths x, 2 minus x minus y divided by 8 fifths minus 6 fifths y. Now, if you notice here, we have a 5 in the denominator for all of them. So that can be struck out if you multiply the top and bottom by 5, right, which you can. All these 5s here are canceled out, and I'm left with 12x, 2 minus x minus y over 8 minus 6y. And then on top of that, I can divide this by 2. I can divide all these here by 2. And I'm left with 6x, 2 minus x minus y. This is 4. This is 3y. So this here is the conditional density function of x given y. Again, all this stuff is just things that you already know. Now you're just applying it to continuous and discrete random variables.